Hello and welcome to this video tutorial. We're going to be looking at the homework solutions for physics homework number 41, work and energy. A couple of things. This is going to have questions revolving around how to do work calculations and how to do kinetic energy calculations. Now, there will be a few times where we have to throw in some constant acceleration type of review, okay? And when we do, we'll just approach that when we need it. So you may want to have your equation sheet set up showing your constant acceleration equations. That way you can follow along with the equations that I'm choosing when we do that part of the problem, okay? So to begin, one of the things that we know for the first, let's see, 6 problems, we are calculating work. And so to calculate the work, now we have one equation that's set up right here, and that works, no pun intended, when the angle between force and displacement is something other than 0. So if you have a force applied at some angle, then of course you're going to use force distance cosine of alpha. But another way to think about it is work is just equal to a parallel component of force times distance. Now, if you looked at it, your parallel component of force is your force times your cosine of the angle times your distance. So this really is the same thing as writing it this way. So keep that in mind. You have multiple options as to how you can do that. Now, also keep in mind when you have a force that is, so say you have a force that is parallel to the direction of displacement, it's just simply going to be work equals positive force times distance. When you have an anti-parallel force like friction, where theta is 180 degrees, then all of a sudden we have work equals negative force times distance. Please have your calculator ready so that we can get started. Number 1, a force of 25 newtons is applied so as to move a 5 kilogram mass of a distance of 20 meters. How much work was done? Okay, so work, it's done by a parallel component of force. The force is going to be the 25 newtons. So we're going to go 25 newtons times the 20 meters. And as you can see, the mass was extraneous information. We didn't need it. That in your calculator, I'll give you a moment. You should have ended up with about 500 joules of work. Pardon me 1 second. We'll just take a moment to set up my solution box. There we go. Okay, number 2. A force of 120 newtons is applied to the front of a sled at an angle of 28 degrees above the horizontal, so as to pull the sled a distance of 165 meters. How much work was done by the applied force? Again, we want a parallel component of force. So you want force cosine 28. Okay, so we could look at this one of two ways. We can go work equals force cosine of 28 times the distance. There's your parallel component of force, right? Or you can simply reorder these and just write it as work equals force distance cosine of 28. As you can see, they're the same thing. So it doesn't really matter what you choose to use. Okay, work equals force times distance times the cosine of the angle. Okay, and you're going to go 120 newtons times the distance of 165 meters times the cosine of 28 degrees. Go ahead and put that in your calculator. We should have ended up with about 17,500. At least it rounds to 17,500. Please make sure that you jot down any question marks next to problems that you still don't understand as we go through our tutorial. Number 3. A sled which has a mass of 45 kilograms is sitting on a horizontal surface. A force of 120 newtons is applied, little typo there, to a rope attached to the front of the sled, such that the angle between the front of the sled and the horizontal is 35 degrees. As a result, the application of this force, the sled is pulled a distance of 500 meters at a relatively constant speed. How much work was done to the sled by the applied force? Okay, well, again, we're going work equals force times distance times the cosine of the angle. We're going to go 120 newtons times 500 meters times the cosine of 35 degrees. Take a moment to put that in your calculator, please. Okay, if we did this correctly, our answer rounds down to about 49,100 joules. Number 4, a rubber stopper which has a mass of 38 grams is being swung in a horizontal circle which has a radius of 1.35 meters. The rubber stopper is measured to complete 10 revolutions in 8.25 seconds. All right, so a couple things. Number 1, we're given a mass in grams, so we got to convert that. So that's going to be 0.038 kilograms. Remember, the decimal has to go 3 to the left. Secondly, we have 10 revolutions in 8.25 seconds. So that kind of makes this, essentially a uniform circular motion problem, right? And in a uniform circular motion problem, those are going to be centripetal force problems, but also to find the speed around, we need the circumference divided by the period. So the period is the time once around the circle. And the period can be found by taking the time for 10 trials and dividing it by 10. And if we divide by 10, we're going to get the time for one revolution, which is 0.825 seconds per one revolution. Okay, 8.25 seconds for 10 revolutions, 0.825 seconds for one revolution. So there's the period we're going to need to plug in. So in part A, we are looking for the speed of the rubber. That should be rubber stopper, not stopped. A lot of typos here. And we can find that speed by taking the circumference of the circular path divided by the period. So we're going to go 2 pi times the radius, which was 1.35, divided by 0.825 seconds. Please take a moment to plug that in your calculator. We should have gotten about a little over 10 meters per second. Okay, now part B says how much force is applied to the string in order to keep the rubber stopper moving in a circular path. So now we're talking about centripetal force, where specifically tension is that centripetal force. Okay, so tension, which is the centripetal force, is equal to mass times v squared divided by the radius. So we're going to go mass times v squared divided by the radius. Now the mass is 0.038 kilograms. The speed we just found to be about 10.3. We're going to square that. And divided by the radius of about 1.35 meters. Please take a moment to put that in your calculator. If you did this right, you should get a little under 3 newtons, about 2.98 newtons. Please practice putting that in your calculator until you can do that correctly yourself. Well, for part C, it says how far will the rubber stopper move with a period of 25 seconds? See, okay, well, take your equation that we have for part A, right, and solve for period. You see, we're going to do that by just switching that out. All right, now what does that mean? We want to know, okay, how far the rubber stopper moved. Essentially, you're looking for the new circumference. But because you're looking for the new circumference, you're going to be looking for, oops, I'm sorry, I solved for the wrong thing. Let me back this up. Sorry about that. Okay, since you have a new circumference, you're going to have a new radius, okay? And what we got to do is we got to find out what that new radius is, and then we'll calculate our new circumference, which would be the distance around, okay? Because the period is 25 seconds. That's the time once around. So if we have the speed, right, we can figure out the distance once around, which is the circumference. All right, so anyway, solve this equation for r. We're going to multiply by t, the period, and divide by 2 pi. So r is equal to v times t over 2 pi. Okay, I'm going to call this r new. This is our new radius. Okay, and now our speed is going to remain the same. So nothing is changing except for the radius, but we're keeping the same speed to make this new period happen. So 10.3 is still our speed. The time period is 25 seconds. We're going to go 10.3 times 25 and divide that by 2 pi. Now, when you do that, you get a new radius of about 41 meters. In other words, big circle. Okay, very big circle. So the distance around would be the new circumference, okay, which is 2 pi times the radius, or 2 pi times 41 meters. And it would take 25 seconds with a 41 meter radius. It would have a complete distance around at a speed of 10.3 meters per second, which is about 22 miles per hour. The circle would travel a full circumference of 258 meters. Part C, how much work is done by the rubber stopper? Well, essentially work is really going to equal 0, okay? And here's basically why. If you think about how this whole process works, you have your rubber stopper is being pulled in by a centripetal force, okay? But its velocity and thus its motion and ultimately its displacement, its instantaneous displacement, are tangential to the force. The angle between them would be 90 degrees. And as you remember, work equals force times distance times the cosine of theta. Well, if the cosine of theta, if theta is 90 degrees, the cosine of theta is 0, which means you end up doing no work. No work is done by a centripetal force. Number 5, how much work would be required to lift a 12 kilogram mass onto a table 1.15 meters high? So essentially, if you found the weight would be 12 kilograms, okay, times 9.8. And when you multiply those, you're going to get 118 newtons. Well, if you're lifting this against its weight, that means that's the force you're applying on it, okay, same as the weight. So the work, right, force times distance would be 118 newtons times the 1.15 meters to lift it. Please take a moment to put that in your calculator. You all should be getting about 136 joules. Number 6, we have a barge. A barge is just a very large boat, okay, and this barge is being pulled along a canal by 2 cables. We're looking at it from the top view, from on top of the barge, okay, and the tension in each cable is 14,000 newtons, and each cable is pulled at an angle of 18 degrees relative to the horizontal. How much work is done in pulling this barge distance of 3 kilometers? Now keep in mind, that distance, we are going to have to deal with that. That distance is going to be 3 meters, okay, or 3,000 meters. Okay, so we'll have to deal with that one. Well, let's find components. We have tension and we have tension. So I've got some gray components that are going vertical like this, and I got some blue components that are going horizontal like that. And I only care about the blue components because the blue components, as you can see, are parallel to the direction of motion that the barge is being displaced. So these, remember, alpha is going to be the same as that angle right there. So this is T cosine alpha, and this is also T cosine alpha. Since there are 2 of them right here, that means your force, your parallel force, is actually 2T cosine alpha. Okay, so we're going to go calculate the work. Work is a parallel force times distance, which would be 2T cosine theta times distance, okay, or 2 times T times distance times the cosine of the angle. We'll just do it that way. So T is 14,000. Okay, distance would be 3,000. So we got to change it to meters. And the angle was 18 degrees. So we're going to go 14,000 times 2 is 28,000 times 3,000 times the cosine of 18 degrees. And if we do that right, you're going to get a lot of work. I mean, think about it. It takes a lot of effort to move that big boat, okay? We're going to get about 7.99. Let's see, 1, 2, 3, 4, 5, 6, so times 10 to the 7 joules. Number 7. Now we begin the kinetic energy calculations. Well, to do that, you're doing 1/2 times m is mass times v squared. V is the velocity squared. When you put this in your calculator, it's often best to take the velocity, square it first, then multiply it times the mass, then divide by 2. That sequence tends to work very well when doing a calculation like this. Okay, so we have a car has mass of 1,250 kilograms, moving with a speed of 26 meters per second. What's the kinetic energy of the car? All right, let's see here. Okay, we're going to go 1/2 mv squared. So 1/2 times the mass times the velocity squared 1250, 26 squared. So square the 26. Okay, now once you've done that, multiply times 1250. Okay, hit equals. Now once you do that, divided by 2, take half. Should be getting somewhere in the neighborhood of about 423,000 joules. Number 8. What will be the kinetic energy of a bullet which has a mass of 22 grams and a velocity of 650 meters per second? Got to take the mass and put it in kilograms. So that would be 0.022 kilograms. Okay, simple plug and chug. So 0.022 kilograms times 650 meters per second. Go ahead and plug that in your calculator. If you did this right, you should come up with a large amount of kinetic energy. Okay, about 4,650 joules. Number 9. How fast must a 4.40 kilogram bowling ball move in order to have a kinetic energy of 185 joules? So now you're solving for speed. So we're going to take our kinetic energy equation and solve for speed. Now, in order to do that, you're going to have to multiply by 2. So we get 2 times the kinetic energy equals mv squared. Then we're going to divide by the mass. And we get 2 times the kinetic energy over the mass equals v squared. Then last step, we'll go ahead and square root. Okay, and we have v isolated. So it's going to be the square root of 2 times the kinetic energy, 185 joules, okay, divided by the mass, which was 4.40 kilograms. Please take a moment to put that in your calculator. I would start by going 2 times 185 equals, divide by 4.4 equals, and then square root that answer. Should get somewhere in the neighborhood of about 9.17 meters per second. All right. Now, in these next set of problems, 10 and 11, we're going to get a sense of, kind of an early sense of how mechanical energy can be conserved and transformed, quite honestly, from one form to another form. But in order to do that, in order to establish that and set it up, we're going to be reviewing and finding our values using old methods, such as constant acceleration equations. Please note that once we get to pH 43 and we start looking at conservation of energy as a way to solve problems, it's a much faster approach than using a combination of Newton's laws, Newton's second law, and constant acceleration equations. Okay, and so you'll find that to be true later on. So for now, we're going to go ahead and kind of solve some of these using older methods, and you'll see that play out too. So number 10, we have a ball which has a mass of 2.4 kilograms is dropped from a building 9.96 meters tall. How long will it take to reach the ground? So the first 2 parts of this, right, are a constant acceleration problem. You're looking for time and you're looking for velocity of an accelerating object. So it's a constant acceleration problem. Okay, list your stuff. We know that y on the ground is 0. We know y naught equals the height, which was 96. Okay, we know v, well, actually, we don't know v. V, that's actually part B. You're looking for the velocity just before it reaches the ground. We know v naught is going to be 0 because of this word right here, dropped. That means it has no velocity to start with. We know the acceleration is due to gravity, so it's going to be negative 9.8 meters per second squared. And we don't know time. That's going to be part A. All right, so my first equation that I'm looking for part A, okay, ladies and gentlemen, I'm looking for an equation that has essentially distance as a function of time. Okay, based on what it gives. I don't know the final velocity yet. Well, that would be the equation y equals y naught plus v naught t plus 1/2 a t squared. Remember, this is 0, v naught t is 0, and so we get 0 equals the height plus 1/2 a t squared. All right, so I'm going to go ahead and subtract the h over to the left, and I get negative h equals 1/2 a t squared. Now, how do we solve this thing for time? We've done this before. It's going to take us 3 steps. First step, multiply by 2 and get rid of the 1/2. Second step, divide by a. That'll help you get rid of the a. Third step, square root. That'll get rid of the radical. And so you end up with time is equal to the square root of negative 2 times h, because there was a negative h there, over a. Okay, now if I went a little bit too fast, okay, for this solving for time, please make sure you come and see me individually, and I'll be happy to help get that straightened out for you. Okay, so now let's go ahead and plug in. We're going to go negative 2 times 96 over negative 9.8. You see the negatives cancel. Please take a moment to put that in your calculator. You should be getting about 4.43 seconds, almost 4.5 seconds to fall. Okay, now I'm looking for velocity as a function of time, because I just found time. Well, I could use this equation right here, in which case I know that's 0. And if I am plugging into that, the acceleration is due to gravity, so negative 9.8 times 4.43 seconds. And I'm going to end up, now I'm going to end up with a negative velocity because it's going in the downward direction, but it's going to be about negative 43.4 meters per second. All right, now part C, what's the kinetic energy of the ball just before reaching the ground? Well, we're going 1/2 times m times v squared. So the mass, if you remember, was 2.40. The speed, you just found it, okay, it's 43.4 meters per second. I can put the negative in if you want, but remember, when you square a negative, it becomes positive anyway. So I'm just going to leave the negative out because it really does no impact. Kinetic energy can never be negative. So go ahead and square your 43.4, okay, multiply it times 2.4, and then take half. We should end up with about 2,260 joules of kinetic energy. Finally, part D, how much work would be needed to lift this back up to the building, the top of the building, at a constant speed? Well, work is equal to a parallel force times distance, and the force you'd be lifting would be the weight. So the mass is 2.4 kilograms times 9.8 times 96. Okay, multiply all these three together. And guess what? We end up with the same thing, meaning the potential energy that it has at the very top is equal to the work required to lift it to get it there, which is also equal to the kinetic energy it's going to have when it reaches the bottom. And finally, number 11. A cart which has a mass of 2.5 kilograms is sitting on top of an inclined plane, which is about 3.30. There's a little bit of a typo there. And that meets with an angle of 18.5 degrees with the horizontal. So how long will it take for the cart to reach the bottom of the incline? How long is time? And what will the velocity be when it reaches the bottom of the incline? Now, we're going to solve these using constant acceleration methods. Please note that you will learn how to find the velocity at the bottom of an incline using conservation of mechanical energy methods later on. Here we go. So constant acceleration. But now I'm going to keep in mind this is going to be in the x direction horizontally. So I've got x, x naught, v, v naught, a, and t. Okay, now x is going to be 3.30 meters. X naught is 0. V, I don't know what that is, but that's part B. V naught is 0 because you're releasing it from rest. Acceleration, I don't know what that is yet. Okay, which means I'm going to need Newton's second law to find acceleration. Okay, we'll get to that in a second. And time, I don't know. That's part A. So before I can figure out time, I need to figure out the acceleration down the incline. So let's use Newton's second law to find acceleration. Okay, what are the forces acting on the cart? So we've got mg going down, and mg sine theta going downhill. Doesn't appear that there's any friction here, so causing force minus opposing force equals ma. The opposing force is going to be nothing, but the causing force is going to be mg sine of the angle equals ma. You can see the m's will cancel, mass independent. And A is going to be G times sine of the angle. So 9.8 times the sine of, what was the angle? 18.5 degrees. And we get about 3.11 meters per second squared. Okay, so using a little bit of Newton's second law, we now have, right, the acceleration. Now we can complete the problem. So to look for time, I'm looking for probably an equation that has position as a function of time. That would be this equation here. X naught is 0, V naught T is 0. So we have X equals 1/2 AT squared. Remember, to solve for time, it's going to take 3 steps. Multiply by 2. Divide by A. And square root. So we have 2 times x, which is going to be 3.30, over the acceleration we just found, 3.11 seconds. Take a moment to put that in your calculator. And we should be getting about almost 1.5, about 1.46 seconds. Well, the speed at the bottom of the hill, we can find that using velocity as a function of time, v equals v naught plus at. Starting from rest, it's going to be a times t. We have 3.11 meters per second squared. That's our a. The t we just found, 1.46 seconds. And we're looking at a speed of about 4.53 meters per second at the bottom. Then finally it says, what is the kinetic energy of the cart when it reaches the bottom? So we're going to go 1/2 times 2.5 times 4.53 squared. So square the 4.53 first, times your 2.5. And then take half. And we're looking at a little over 25 joules, about 25.7 joules.